last video, we introduced the concept of a vector. Remember that a vector is anything that has both a magnitude or size and a direction. So we looked at this map of Ender the puppy's trip around Ms. Rintoul's front yard and how each stage of his trip has a magnitude, an amount, and a direction that it's pointing. And we noticed that each of the arrows is laid down so the tip of one arrow touches the tail of the next arrow. And then we have another tip to tail, and you can imagine Ender the puppy walking around the yard, maybe peeing on the fire hydrant, coming to a stop. That's how we're going to add our vectors. The tip of each arrow needs to touch the tail of the next one. And the result of this vector addition is how far we are from where we started and in what direction. In the case of things like meters or kilometers, we call this a displacement. And again, our final vector, our displacement vector, needs to have both a magnitude and amount that we could measure with a ruler, and a direction that has often a degree, but could also be north, south, east, west, left, right, up, down. Anything like that would count as a direction. So in this case, we are looking at 53 degrees. And then we talked about, well, how do we name this direction? Well, we say, well, we start our rotation from a certain direction, and then we rotate towards another direction. So my rotation starts north, and I'm rotating towards the east. So I end up with a direction that is 53 degrees to the east of north. And that was how we wrote our answer down below. We said this was 53 degrees east of north. We tend to write our vector symbols with an arrow over the top to show that it's a vector. And then we also contrasted vectors with something called scalars, which are what we're more used to adding together, which are just basically numbers. They don't have a direction. So we had things like time, distance, speed, energy, mass is in kilograms, or volume in liters, and we just basically add those numbers. But when we're adding vectors, our life gets a little more complicated. So we need to draw out our vectors when we want to add vectors. So this is 3 centimeters plus 2 centimeters. And to find out what that equals, again, we lay our vectors tip to tail. The tip of one touches the tail of the next one. And our result of our addition goes from the very beginning where we started to where we finished. And we say, okay, how long is that? Again, you could take out your ruler, measure that, and in what direction? That would be 5 centimeters to the east. When we have vectors in opposite directions, again, we draw them tip to tail, so the tip of one touches the tail of the next one. And our resultant goes again from start to finish. But when our vectors are in opposite directions, we actually end up having an arrow at the end that's shorter than the ones that we started with. So we took our 3 centimeters minus our 2 centimeters, and all we ended up with 1 centimeter. And again, start to finish ends up pointing, we're still to the east of where we started, so this would be 1 centimeter east. And our life gets more complicated when we have vectors at right angles to each other or even strange angles to each other. But again, the principle stays the same. We're going to add them tip to tail, so the tip of one vector touches the tail of the next vector. And we draw our resultant vector from start to finish. And again, I could take out my ruler and measure how long this is, or I could also calculate using Pythagoras. 3 squared plus 2 squared square root gives me the 3.6 centimeters. And I could take out my protractor to measure this angle to see how much north of east I am, which is what we looked at in the next section. So we looked at how do I name each of these vectors that are already drawn for me. I need to know the angle of rotation. I need to know where I'm starting my rotation, and I need to know in what direction I'm rotating. So my angle of rotation, the start of my rotation is actually the second letter because I end up not being at east, but I end up rotating to the north of east. And my first letter is the direction that I'm rotating. And we said there are actually 2 ways of naming every single vector because my 2 angles here are complementary. They should add to 90 degrees. So if I started at north and rotated, I would rotate through a different angle, in this case 62 degrees, and I would change how I name that, so 62 degrees east of north, because I started at north and rotated towards the east. So, quick recap. How am I going to add 5 meters east and 3 meters east? Well, the first thing I'm going to do is more or less draw what that would look like. So 5 meters east would be pointing towards the right. This is my 5 meters east. And the second vector, 3 meters east, oops, I like to use rulers. 3 meters east is going to be shorter than my 5 meters east, but still point in the same direction. So, if I want to add these two together, what does that equal? If you've been following along and remembering from what we did last video, you should be able to draw the diagram and figure out your resultant. So pause your video now, see if you can draw the diagram, and then come back and see how you did. So here it is. We draw my 5 meters east, tip to tail with my 3 meters east, and then my resultant vector is going to be from my start to where I finish. And the whole length of that is going to go down the 5 meters, down the 3 meters, so we're going to add them together to get me 8 meters, and the direction from start to finish is still east. So I would be 8 meters east of where I started from. Example number 3, 15 newtons left. So again, let me see if I can draw that. 15 newtons left. It's going to go this way. Plus 28 newtons right. Okay, 28 newtons right. I know that's going to be longer than my 15 newtons. So something like that. So I have here 15 newtons left. So I have my 15 newtons, and then I've got my 28 newtons right. And I wanted to add them together. See if you can figure out how to draw this vector diagram. Pause your video, come back and see how you did. And there you have it. So start out by drawing your 15 newtons to the left. Tip to tail with that, your 28 newtons to the right. And your resultant vector, your start to finish, will also point to the right. Because they're in opposite directions, I'm going to end up with a vector that's shorter than my longest vector here, the 28. So 28 minus 15 gives me a resultant of 13. And it's going to be 13 newtons right. That would be my final answer. So we've been saying this out loud a lot, but the third vector that I'm drawing, the red vector every time, represents the sum of the first two vectors. And it is called the resultant. So even though the result may be smaller than my original vectors, it's still considered a sum. It's still considered vector addition. So that's adding vectors in what we call one dimension, where we're really only going along a straight line in any way. Now we're going to take that to the next level, involve your trigonometry skills, your Pythagorean theorem, and your SOHCAHTOA to add vectors in 2 dimensions. What happens when my vectors are north and east, or north and west, or south and east? What do we do then? Well, we're going to follow the same general principles. We represent the vectors with arrows. One way of adding vectors would be to carefully draw them onto scale using graph paper, a ruler, and a protractor, and then carefully measure the distance between them. The problem with that method is that you have to be very, very, very careful about your angles, about your lengths that you draw things. So that's why we're actually going to end up not using this method super much, but relying more on trigonometry to get us our exact answers. So again, we've been saying this all along, but here's highlighting the result. To add 2 vectors, we draw them tip to tail, and the resultant, which I'm going to label R, is the line from the start of the first vector to the finish of the last vector, start to finish. Let's see some examples. Example number 4. John travels 10 kilometers west, then 18 kilometers north. What is his resultant displacement? So again, I could take out my graph paper and make this like 1 centimeter is 1 kilometer and draw something 10 centimeters, 18 centimeters. That would take up most of my paper. That's okay. then draw my resultant. Instead of doing a scale diagram and taking a protractor to measure my angle, I'm going to use my trig. I still need the diagram, but the exact lengths that I draw things isn't going to be as critical. So what I'm adding here, I'm first going to just draw these, is 10 kilometers west. So 10 kilometers to the west would look something like that. And I want to add to that, I like switching colors just so I can keep track of things, 18 kilometers north. So I'm going to draw in, should be longer than my 10 kilometers, but it doesn't matter if I've got things exactly to scale. If I've got my 10 kilometers and my 18 kilometers exactly, as long as the 18 is longer than the 10, I'm happy. And I want to find the result, which would be if I put these tip to tail and connected start to finish. So to do that, I need my tip here. I need my green vector basically to start at this tip. So in order to be able to do that, I'm going to move the 10 kilometers down. I'm going to redraw everything over here. This is where my actual vector diagram is going. So here's again my 10 kilometers. But I put it down low so that I could go tip to tail. Here's my green vector, tip to tail, 18 kilometers north. So again, tip of my blue vector touches the tail of my green vector. And this is where I started, right here at the tail of the blue vector, and this is where I finished right at the tip of the green vector. So my resultant is going to complete the triangle from start to finish. Put an arrowhead on it. That arrowhead is going to be important. So I want to know how long is this resultant. I'm going to call it R. The result of adding 10 kilometers west and 18 kilometers north. Well, what I'm looking at right here, right now, is just a right triangle. And we know with right triangles, we can always use Pythagorean theorem to find my hypotenuse. So that's exactly what I'm going to do. So I know a squared plus b squared equals c squared. So in this case, that's going to be 10 squared plus 18 squared equals r squared. And I'm going to solve for r. So take the square root of both sides. Take the square root of both sides, plug that into your calculator, and that should give you the magnitude, the size of my resultant. When I do that, my calculator tells me my answer is 20.59126028. How many decibels am I going to write? Remember, your rule of thumb is going to be to always write 2 or 3 sig figs. So if I was going to round to 2 sig figs, 2 would be my first sig fig, the 0 here would be my second sig fig because there's a decimal in my number and it's in the middle. So 2, 0, this would be my second sig fig. So to 2 sig figs, this would be 21. And to 3 sig figs, this would be 20.6. So either of those is fine, either 21 or 20.6. I'm going to keep 3 just to be on the safe side. So 20.6 is my R. Kilometers. I'm not going to put the arrow over the top yet because I don't know the direction. So this is just the magnitude of my R. I eventually need magnitude and direction. So magnitude 20.6. Direction. Well, what direction am I going in? Which angle am I going to want? Now, if I look back at what we did yesterday, you'll notice that all the angles that we were interested in or looking at are at the tail of my vector, always where my vector starts, where it originates. So that's going to be true in all my vector diagrams as well. I want the angle where the vector starts. So let's see how that works. So this vector, so I need the angle at the tail of my vector, which is right down here. This is the angle that I'm looking for. I'm going to call that angle theta, just so I know where I'm referring back to. So, in order to find angle theta, I need SOHCAHTOA. In this case, I technically have all 3 sides, but my hypotenuse is an angle or a side that I've calculated. So I'm going to avoid using any calculated numbers, even though I found it to be 2.6, because I know this is a rounded number. This 2.6 wasn't exact. I'd have to pull up on my calculator exactly what I had. So I'm going to stick to the 18 and the 10. And that gives me, this is my opposite side and my adjacent side, so that means I'm looking at TOA. So let's go with tan of my angle, theta, is opposite 18 over 10, adjacent 10. And you know that to find the actual angle, I would take the inverse tan of both sides. So I'm just going to do that on my calculator without showing all the steps here. But if I take the inverse tan of 18 over 10, what angle does that get me? That gets me an angle of 60.9453959. And I want to round that to, again, 2 or 3 sig figs. Because I started with 3 sig figs with my R, I'm going to stick to 3 sig figs. But if you did 21 kilometers for your magnitude, then you could do 2 sig figs here. So this is either going to be 61 degrees or 60.9 degrees, depending on 2 or 3 sig figs. I'm going to use the 60.9. So here we go. So 60.9 degrees. And I'm going to write my total final answer all as one big long R with an arrow. That's my vector R. This is what I'm looking for, is 20.6 kilometers, 60.9 degrees. And now I have to think about what direction am I rotating from. So my cardinal direction that I'm starting at looks like this blue line, which would be to the west. So I'm going to rotate from the west, so that tells me I'm looking for something of west, rotating from west. And I'm rotating towards the north. So my other letter, so I start at west, rotating towards the north, is going to be north of west. And that would be here, my final and full answer. So again, think back to what we did. We took our original vectors and redrew them tip to tail so that the tip of the blue vector touches the tail of the green vector. Then we drew in our resultant to get our hypotenuse. We used Pythagorean theorem to find the magnitude of the resultant. And we used tangent, inverse tangent actually, to find the degrees. Finished up by putting everything together and then thinking about the rotation. We started pointing to the west, rotated towards the north, so we're ending up north of west. So a couple steps to remember, but you can do it. And this is how we're going to do vector addition for every single kind of vector. So this was displacement vectors. The next one we're going to look at is forces. If it's velocity, it all works the same way. Anything that's a vector, we're going to add the same way. So let's take a look at example number 5. I have force number 1 is 10 newtons due east. I'm going to add to that force number 2, that is 6 newtons due south. And I want to find the resultant force. So again, I'm going to draw my vectors really quick. So 10 newtons east, something like that. I want to add to that 6 newtons south, 6 newtons south, whoops, with a ruler, going to be shorter than the 10. And I want to know what that equals. So see if you can draw your vector diagram, use Pythagoras to find your hypotenuse, and use SOHCAHTOA to find your angle. Pause your video now, try it out, come back and see how you did. So you redraw your vectors, connect start to finish for your resultant, use Pythagoras to find your magnitude and tangent to find your direction, put it all together, thinking about the direction of rotation, and you are golden. Example number 6. A plane is flying due north at 132 meters per second. A crosswind is blowing due east at 44 meters per second. What is the plane's resultant velocity relative to the ground? Okay, we're dealing with vectors. We're talking velocity, speeds, and directions. So see if you can do this one totally on your own. Pause your video, try it out, then come back and we'll talk it through. All right, 132 meters per second due north. Vector looks something like this. I have a crosswind blowing due east at 44 meters per second. I'm going to draw that right away, tip to tail. Due east, quite a bit smaller than my 132. Here's my 44. And my resultant is going to be all the way from where I started drawing to where I finished drawing. This is my resultant velocity. Again, to find my magnitude, I'm going to use Pythagoras, so square root of a squared plus b squared, so 132 squared plus 44 squared. So that would get me 139 meters per second. And I want to find always the angle at the tail where I started my initial. So that's going to give me a tangent of theta equals 44 over 132. If I inverse tan that, gives me an angle theta of 18.4 degrees. Put it all together for my final answer. R equals, our arrow is 139 meters per second at 18.4 degrees. And thinking rotation now, starting at north, rotating towards the east, this is going to be east of north. Alrighty, little cartoon to finish you off. This is Foxtrot by Bill Ammond. It says here, Jason, what pattern did I tell you to run? You said go 10 yards out, then 10 yards to the right. And what pattern did you run? I went 10 root 2 yards at a 45-degree angle. And are they the same thing? If you add the vectors, sure. This is football, not math class. Why do you think I ran it to do decimal places? And one more. Okay, here's the play. Go 40 yards downfield, then turn left and go 20 yards. Then turn right and go 25 yards. Then turn right again and go 30 yards. There you see the vector diagram. That's what's going on. Then turn right and go 30 yards. Then turn left and go 10 yards. Then turn left and go 15 yards. Then turn left and go 20 yards. Who can ever remember a play that long? Then turn left and go 50 yards, and I'll hit you with the ball. And the friend is doing the math, adding up the vectors in his head, and he says, wait a second, won't I be right back where I started? And the little guy says, I can't throw very far. And the friend says, okay, here's a new play. And he takes the football. I never get to be quarterback. So there you have it, some vector humor. Good luck with the homework. And as always, I'm available for questions.